Hey, John here. Let's talk about this thing called a heap. What are they? What are they used for? Why do we care? All right. Now, we've already discussed how a queue works, right? It's a first in, first out data structure. The first thing you put in is the first thing you get out. You can peek at the front of the queue and you can put things in the back of the queue. But there's no way to really modify the queue once it's going, and it doesn't handle this concept of like prioritized events, right? So you fill a bunch of things in the back of the queue, and let's say you have something that's a high priority, and then 3 low priorities, and then another high priority. Well, they're going to come out in that same order if you just use a regular old queue. But if you have what we call a priority queue, which we'll see can be built using a heap, you can tell the second of the 2 high priority items to move in front of any low priority items that you might have already put in the queue. Now, like I said, you can create this thing called a priority queue using a heap, and a lot of times people just call a priority queue a heap because it is one of the most incredibly common ways to implement something called a priority queue. So let's talk about a priority queue for a minute before we get too far along. Now, a priority queue looks just like a queue. They go in one end, come out the other. Now, the idea of deleting min has to do with deleting the minimum value of a priority, right? So if your priority 1 is the top priority, it is the lowest number, okay? So it's not the minimum priority, it's the highest priority minimum, like key value kind of a situation, all right? So these are the kind of operations you would do on a priority queue. Obviously, when you would insert an item, you would enqueue it into the queue, right? You put it into the queue. You would obviously have to include some sort of the priority value along with it, okay? So that the delete min knows which one is the highest priority. Now we could implement a priority queue using a linked list. All right, this is really no big deal. Just create a linked list that fills up with a bunch of items, and every time you want to go find the highest priority or the one with the minimum value, you just go through the list and find it, right? But that would be a linear probe, and it would take order n operations to find the one with the highest priority, because you don't really know where it could be. You actually have to check every item in the list every time you want to find the one with the top priority. Now, you could implement it using a linked list, and you could take one or the other, right? You could just say, hey, put all the new items in one end of the list, okay? Or you could insert them and sort them, like an insertion sort, one at a time. Find the place where this next item belongs in that linked list, and you could put it there. Okay. Now, depending on how you insert them, whether you keep it sorted or not, you would change the way that the deletion would work. Okay. If you don't sort them when you insert it, insertions are real easy. Then you just poke it into one end, right? But then when you remove something in an unsorted list, you have to check every single element every single time. But if you keep it sorted all the time, the delete min just only has to take it from the end with the highest priority item sitting on it. But the insertions have to be sorted every time they get put in there. So if you need to sort things in a linked list, you're doing a linear probe to figure out where to put it, okay? And since it's already sorted, if you start with the maximum priority and you just go through each list node one at a time until you find the place to put the current element that you want to insert, you stop looking right then and there. One could argue there's less operations if you sort it while doing the insertions rather than leaving it unsorted and then having to find a needle in a haystack every time you want to find the high priority, delete it and remove it. But as we'll see, there's other ways to do this, right? I mean, we found that linear probes and linked lists are not always optimal. You could always use a binary search tree or AVL tree or a red-black tree to keep the thing relatively optimized. And that way you could always get delete min because it's sorted. It would run in order log n time because it's always the leftmost node, right? In fact, you don't really even need to search for it. You can just hard code that routine to just wander down the left side of the tree to find the leftmost node every time you want to delete it. insertion naturally occurs, right? Because you're using order n time to search down through your tree to figure out where to put the new nodes. Not a problem. But keep in mind, a binary search tree sorts every single element all the time. What we really need to do is only keep track of the one that is the highest priority that will next be needed. So we can kind of optimize the situation here using what's called a binary heap. So let's look at the properties then of a heap. What is a heap? It's a binary tree. Okay? That is either complete or almost complete. That's what the narrative over here means. And these are the some diagrams of this is not a complete tree, so this could never be a heap, no matter what the values of its keys are. Okay, this is a complete tree here, and this one is almost complete, right? Because almost complete means all nodes at all levels are present except for the far right side of the bottom row of leaves. So what is the ordering property? Okay, the goal is to make sure that delete min is always as fast as possible. And to make that happen, we want the root of the tree to be the smallest value. And the root of all subtrees have to maintain that property too. This is the algorithm that creates this is called heapify, all right? So this is a heap. Notice this is not a binary search tree. It doesn't fit our other notions of like, you know, if we're going to do it an in-ordered, pre-order, or post-order traversal, no, you're not going to get the keys in a sorted order that way. A heap works a little bit differently. This node here is a key that has less than its children nodes. This node here has a key that's less than its children nodes. This node here has a key that's less of its children nodes. That makes it a heap, okay? This one here, why is it not a heap? Because 4 is not less than both of its child nodes, right? Because 4 is greater than 2. So that this can't be a heap. And 8 is not less than either of these children nodes. So this is definitely not a heap. So is this a heap? Is 5 less than 2 and 6? Not really. That doesn't work either, okay? And even if it was, 2 is not less than 1. So yeah, this fails in 2 different ways. So how then do you insert an element into a heap? Okay, what you do is you place the new element, say X, is the next available location in the tree. And that would be, if we go back a little bit, one of these holes down here, right? So you're going to fill this tree up from the top down and left to right. So the next hole will be this right child of this node here, because we always want to be almost complete. You cannot put it over here because that would violate the definition of an almost complete tree. Okay, almost complete means all nodes at all levels except for the rightmost nodes on the bottom level here. The rightmost leaves can be missing. So why do we do that? Because we need to maintain the structure that is an almost complete tree. So what do you do after that? You need to make sure that the key is elevated up into the tree, into the right position where it belongs to maintain what we call our heap order, right? Now, a heap can either be a minimum heap or a maximum heap. You know, obviously, sometimes you want the biggest number on the top, other times you want the littlest number on the top. So it really doesn't matter which kind of tree we're dealing with here. We just need to know, should we be using greater than or less than when we ask about the values in the upper levels compared to the lower levels. So let's look at an example on how to actually do the insertion here with a little bit closer view, all right? Given a tree like this, right? This is an almost complete tree, and let's assume that this node here, this leaf down here is missing, all right? This would be the hole that we mentioned earlier. So if you want to insert a new element into the tree, you just simply put it there. Now, if the key value that you insert down here turns out to violate the sort order of the heap, you have to do what we call sift it up to where it belongs. So, for example, let's insert a 14 into this tree right here. So there's this hole right there. That one there is going to become the 14. All right? Now we got to start asking our questions. Does it belong there? if this is a min heap, which it must be, because 13 was less than 21 and 16 and so on. If we put a 14 down here, this is not a min heap anymore because it's too small. It has to be greater than 31 if it belongs down there, right? So we can swap these two. And you do this by using a routine called sift up, okay? Now you do it again. Is 14 supposed to be a child of 21? I submit no, not on a min heap. So we got to sift it up again. You swap these two guys, right? So now you could ask the question, does it belong here or can it go here? Well, at this point, yes, because it is greater than 13. So what do we know so far? The structured property of a min heap or a max heap is that you've got a binary tree that's completely filled or almost complete, okay? The order property is such that it ensures that the smallest key can be accessed as quickly as possible. To do this, the root has to be the minimum value of all the elements in the entire tree. And as I've mentioned before, you can create a min heap and you can also create a max heap, right? The comparable here refers to whether you're asking if each element on the top is greater than its children or less than its children, okay? So in contrast to a min heap, a max heap, what is that thing going to look like? Well, now we got the same structure. Binary tree, almost complete. The heap order property, in this case, because it's a max heap, it allows us to have a function called delete max, and that it is as fast as possible. And therefore, the root has to be the largest value of all the keys, of all the nodes in the tree. Now, if we look at a max heap and we want to insert a new node whose key is 14, we find the first available location in this tree, that hole right there, stick it in there, and then we ask, is that where it belongs? Now remember, this is a max heap. So the way this has to work is this value of this key here has to be less than the value of its parent instead of greater than, okay? And in this case, yes, it is, so we're done. What if we want to insert a 45 now? Where does that thing go? Well, again, we need an almost complete tree, so it should go over here as a left child of 16. There's the hole, put in the value, ask the question again, is that where it belongs? Max heap. Is this key less than that one? No, you have to sift it up. So you swap these two. Ask it again. Is this key here less than 19? The answer is no. So you need to sift it up again. Ask the same question. Is 45 less than 68? The answer is yes. This is where it belongs, okay? So how can we store these? All right? So one of the big wins about a heap, all right? You can use a heap to store a binary tree. I mentioned this before in the discussion on how to do a level order traversal of a binary tree. Because one thing you can do in order to traverse a tree in level order is just simply convert it into a heap and then iterate through all the elements in the heap from left to right. Because a heap, as we'll see here, is just an array. Now, there's two ways to do this, all right? Before we dive in too much, notice this array, we're not using element 0, okay? The math, if you use an array in the way I'm talking about in these slides here, works ever so slightly different than it does for other examples you'll find on the internet. So I want to make really sure we understand there's two basic ways to do this. In one way, you just don't use element number 0. The other way, you do use element 0. You change the math ever so slightly when it comes to asking the question, where is the children of a given node? Okay? So in this notation, any element in the array at position I, okay, so where I is 1, say, for the root, that element's left child will then be at 2 times I, and the right child will be at position 2i plus 1. So how does that thing work? Well, if if I want to say, what are the children of this element here, A, which happens to be the root, right? The root in this notation is always in index number 1, okay, position 1 here. Therefore, the left child is at 1 times 2, which is 2, right here. It better be a B, right? Oops, I don't want to edit my slide. Better undo that. Yes, and it is. Here's the left child of A. It's B, and B is right there at element 2. Where's the right child? It's at 2 times I plus 1, which is going to be 3, and you find element C stored right in here, okay? Now, why do we store them in an array like this? Why don't you just use a tree? Well, a tree is usually built out of node objects that have links, like a parent pointer and a left and right child pointer and things like that. On a 64-bit system, which most of our PCs are nowadays, every pointer requires 8 bytes. So if you put a single integer or a character in a node like we're showing here, that means a 1-byte character has at least the overhead of, the left and right child pointers and or the parent pointer, okay? Which could be as much as 8, 16, or 24 bytes worth of pointers there to represent 1 byte of data. All right? You throw away all the pointers and store it in an array like this. The only thing in this array, then, are the values of those nodes, or its keys. In this case, that 1 byte, okay? You save a huge amount of memory storing it this way is the point, and all you got to do is keep in mind how you navigate from the parent node to the child nodes. Now let's visit really quick over to Wikipedia, which uses a different notation. As you can see right here, this array notation that they have down here, notice the root in this tree is stored at element 0. Let's zoom in on this image here. Okay, see how element 0 in this array has the root in it, in contrast to element 1 in the slide deck that I'm using right now. Okay, the only difference if you use this method is the math on how you find the child nodes. Okay, and if we scroll through the text here, you'll see buried right here in this notation, any given node at index I, in this case the children of the root, where the root is say at 0, okay, the children are at 2i plus 1 for the left child and 2i plus 2 for the right child, which is only slightly different than this, where we see that the left child is at 2i, you could say 2i plus 0, and the right child is at 2i plus 1, okay? So if you're going to start at 0, you just have to add an extra 1 when you're calculating the children node positions. The one on Wikipedia said 2i plus 1 and 2i plus 2, or 2i plus 0 and 2i plus 1 here, okay? And I want to hit this point hard because if you look around the internet, you'll see 2 different ways of doing this, all right? This math here is based on not putting an element in the 0 location of your array. So to work a few examples, where's the left child of B? Well, if B is at index 2 here, we just say 2i, which is 4. That would be D, right? And clearly we can see that D is the left child of B, right? Who's the right child of C? Well, C here is at index number 3. The right child would be 2 times 3 plus 1, which is 7, which is G. Okay? And we can see that is, in fact, the right child of C. So what's wrong with this picture? All right, what happens if you insert until you run out of the you run off the end of this array, right? Then you need a bigger array. Now, if you store this in a vector or something like that, you can always resize it and get around that problem. But usually what you'd like to do is just create one that's big enough for your needs from the get-go so that doesn't happen. And yes, you're wasting this extra space down here. Much as I was concerned about all the extra space to hold pointers, if your element keys and values are small, well, if those element keys and values are big, or gigantic, what if they're all a megabyte each? Then storing it in an array might not be optimal. Again, you have to take the specific needs for your application in mind and not just blindly run off and say, oh, they're always done this way. No, they're not, okay? You need to keep in mind what's important with respect to the application you're solving and the nature of its data. So the physical structure of the tree, right, is supposed to look like this, and here are all of its keys. We know this is a max heap because the node value here, the key of this node is always greater than its two children. And that is recursively true, that this node here has a key that's greater of its children, and the node here has a key that's greater than its children, and so on. All right? So the question is then, how do we fill this thing in? Well, we know the root goes in here, at element number 1, right? And you know that its left child goes at this index times 2, which would be 2. So you should see a 68 here. 65 should go here. What goes in here? That's the right child of 1, because that's 2 times 1 plus 1, which is 3. That's where this key of this node goes, all right? As you fill this thing in, it should look like this, okay? So, this 19, the left child of number 45 up there, right? 45 is that element whose index is 3. Its left child goes at 2 times 3, which is 6, which is why we see the 19 right there, okay? What about the left child of 19? Well, it would be going in at 2 times 6, which would be element 12 over here if we continue on, okay? Or, I always cheat and just go and do a level order left to right traversal in my head. 68, 65, 45, right? 68, 65, 45. Then we go to the next level, 26, 32, right? 26, 32. And then 19 and 13 like this. Boom, boom. And this is what I walked through when I was talking about binary trees early on, when I was saying, hey, here's a neat way to do a level order traversal. Convert the binary tree into what we now know is called a heap, and then just go through the heap in order and print out all the elements, okay? So we've looked at how to insert elements into our heap. How do we remove them? And how do we maintain the order requirements for a heap? Well, given this heap, let's say we want to delete 13 here, okay? You're always going to, when you're dealing with a priority queue, you're always going to be deleting from the root. You're going to insert down here, sift up, and then you're going to be deleting from the root. So once you remove the root, what do? Because we've removed a node, we know that in order to maintain an almost complete binary tree, this node down here has to disappear. To fill this one in with something means this one has to go away. So what we can do is just move this one up here and then fix it, okay? So move the 31 up there. And then ask, is this okay? Well, we're dealing with a min heap here, and we just deleted the minimum key, right? So is this the new minimum? No, right? Because in a min heap, the one on the top, the parent, has to always be less than the children keys. Now, to decide what to do with this, we first ask, which of the children of this node here has the smallest key? And we see that that is 14. That node, 14, must become the new root. Because if it was a min heap before, and it has to remain a min heap as we proceed, the smallest key has to replace the one that was removed. And because the thing was in heap order before, the next smallest keys to what used to be in this tree has to be at this level underneath the old root. So the smallest one needs to move up to the root. In order to make that happen, we need to move the incorrect node has to move down and take its place. All right? This is called sift down. All right? It didn't belong up there. What do? I move it in, I swap locations with whatever child has the smallest key, because I'm doing a delete min. If it was a max, you'd do it the other way around, okay? And once it's there, you do the same thing. Well, which one of the children is the smallest key? It's this one here. Then you ask, is the key here less than the key down here? And if the answer is yes, you need to sift down. Okay? And then you ask the same question again. Is this key less than its children keys? Well, this one has been removed at this point, and there's the only one left. And is it less than that? Yes, it is. Therefore, we know we're done. Okay? So let's do the same example with a delete max just to drive the point home. Whenever you delete an element from a priority queue, you're always going to delete the root node out of the heap that sits behind it. So a delete max will return the value of the root node, okay, which would be 68. And because doing that leaves us with a hole, what do? We do the exact same thing with delete min, but we're dealing with the maximums, right? Got to maintain an almost complete tree, so this node right here gets moved up here, and then we sift it down as appropriate, okay? We see that it moves up there. And just like before, because we're dealing with a max heap this time, we use maximums. So what should be the new root? Well, 65 or 45. 65 is bigger. So let's see if 16 is less than 65. It is, so we need to swap those, okay? So you're going to reverse these guys. And we repeat that process. Which one of the children nodes is the biggest key? Well, that'll be 32. We're going to compare these two, right? Is 16 less than 32? Yes, it is. We need to sift it down. Now, we're going to ask, which of its children nodes has the largest key? Well, that would be the one down here. Again, is 16 less than 31? The answer is yes. It has to sift down, okay? It has no children anymore, so you're done. That's where it belongs, okay? So we've moved the 16 from here. We put it up here, and then we've sifted it back down to here. So to summarize, when you're going to delete the min-max value from either a min or a max tree, right? What do? You take the last element in the almost complete tree and you move it up into the root. Then you sift it down by heapifying your tree. Now, before we go, let's just look at some pseudocode for the insert process. All right, because we're going to express the pseudocode here in terms of the heap as it is stored in array form, not in a tree over here, okay? So let's say we want to insert a new element into our heap. And then our heap for this tree looks like this array up here, okay? And we're going to make a couple of assumptions here. That current size is the size of the heap, right? That's the number of elements in here. And we're going to assume that there's always at least one element in the heap in order to do this algorithm here. You're going to have to deal with the case where there's no elements in your heap. I think that's pretty darn simple. If you want to insert an element into a heap that has nothing, you just pop it right into element one there and you're done. That special case. In the more general case, what happens is the new hole at the end of your heap, obviously over here, would be at this 10 over here, right? It's going to be at current size plus 1, right? So you can just say plus current size to move current size over here to the 10 and say that's where the hole's going to be. That's where the node that reflects this element right here is supposed to go. Now look and see how this code actually works in here. The ax that's going to be inserted is actually not stored into the array that holds your heap until we're done with this whole loop in here, okay? Now the notation used in these slides, we're going to show the 14 in here as we go, but we're really not going to store it into the array until the bottom. You'll see this is a nice optimization. It allows you to do a swap without really doing a swap, right? Well, watch what happens here, okay? We've identified where the hole is down here for the new element to go, all right? Now we're going to show the 14 in red. But we didn't store it in there because this code did not say to do so yet. We're just showing you where it would go if we were done now, okay? So what do? We ask, is the 14... the new thing we're going to insert, is it less than the heap at the element whole over 2, and this is an integer division. So it's really the floor of, because whole is at 10 right now, of 10 divided by 2, which comes out to be an even 5 right now, okay? So what are we doing here? We need to move up and ask, should it move up here into its parent position? And due to the nature of how a heap works, using this notation, and remember there's 2 different notations, the parent of any node is at the index number divided by 2. So we want to ask, look, does the 14 belong down here? Well, obviously the answer is no if this is supposed to be a min heap, right? Because it has to be, it can't go as a child of a node whose key is bigger, okay? So we go over here to 10 divided by 2, and that's where the 31 key is when it's stored in this array. That's why this is whole over 2 right here. And we ask, is x less than that value? Well, in this case, it is. So what we're going to do is we need to move the 31 over to the whole at 10. All right? So heap whole equals heap of whole over 2. That's going to move the 31 over here. And as the slide will show, okay, the 31 moved over here, and 14, where it would go if we were done, would end up in position 5 here, okay? And you can see over here, we've swapped them, okay? But we really didn't swap them. All we did is copy the 31 from 5 over to 10 here. Then we proceed to divide the current whole pointer by 2, so it follows where 14 would go as we go along here, all right? Then we go around the loop and we do it again, okay? Is 14 supposed to be the child of 21? No. So you see those end up getting swapped again, all right? Now you ask, is 14 supposed to be a child of 13? Well, the answer is yes, so we know we're done now, and that's the final resting place. Now, this is the only time we actually store the 14 into this data structure. All right. Now keep in mind that saves you from actually having to swap 2 items, right? With a temporary, copy this, and with temporary, copy that one over here, copy the temporary down. You're wasting 2/3 of your CPU time is wasted if you literally swap. If you just move the parent node down to the child whole position repeatedly, until you find out the position where the new element is supposed to be inserted, and then only then do you actually store it in the structure like we did in element 2 over here. You've saved all that extra CPU time. Now you might say, who cares when you only have 5 or 10 elements in your heap? But if you have millions, it makes a big difference. 2/3 of your time is wasted, right? I wouldn't want to waste 2/3 of my life, so why are we wasting 2/3 of the runtime of this program, okay? That's why you don't store it into the array that holds the heap until down here when the loop is done. So, what do we got? What's wrong with this code, right? Well, it's the same problem we had before. This code doesn't actually ask, is the array big enough to hold the new element? And what if we insert another element now? Well, there's nowhere for it to go. So this is left as a student to make sure that you can deal with these sorts of things. Now, obviously, one way to do it would be to use a regular C++ vector in here instead of an array so that you can grow it as needed and always have a place to append a new element. So I hope this gives you a good understanding of how these things work, how you can implement insert. I'll leave delete as a task for the student. Thanks for watching. See you next time.